Challenge problems number 9, and this is a loaded problem. Let's take a look at it. And here we go. We have some silver nitrate. Looks like we got milliliters in molarity, and we got milliliters in molarity of aluminum chloride. And we're asked to write a molecular and ionic equation, identify the precipitate, find the mass of the precipitate, find the concentration of each ion left in solution. Whoa, that seems like a lot of stuff. Okay, let's break it down and look at coming up with a molecular equation, which I do here. And the ionic equation, if you understand what's going on and keep track of stuff, you certainly can write it out. But if you understand how ions work off the molecular equation, this really wouldn't be necessary to write the ionic equation. But let's take a look here. We have AgNO3, and I'm not going to do much with this. I'm just going to give this, which is silver nitrate. Silver is +1, NO3 is -1. Aluminum is +3, Cl is -1. So this is a formula for aluminum chloride. Then we get AgCl, which is +1, -1, and aluminum nitrate, which is +3 and -1. I think we might have done this one in experiment A. Anyway, the net ionic equations. So we get this, and we ultimately balance the equation, and we find out the ratio is 3:1 to 3:1. How do we know that silver is a solid and aluminum nitrate's aqueous? Well, if I looked at my common ion chart, I would see in rule number 3 that all nitrates are soluble, so that makes us aqueous. In rule number 5, chloride with silver is solid. In both of these solutions end up being aqueous. If we look those up, we're really given that because we have the solutions and the molarities. Okay, what does this end up looking like? This ends up looking like something like this at the end of the day. AgCl is your precipitate, and we have spectator ions floating around. But because we're given reactants of a couple things, we probably have some excess ions, and we'll come back to look at why we chose aluminum chloride as the excess ions in this case. So it's like what we've drawn before in the product. The precipitate sinks to the bottom, the spectator ions remain, but we do have excess ions that we have to account for too, which complicates things, and we'll want to figure that out. Okay, well, I have 2 reactants, and I'm given liters in molarity for both of them. And unless you have the perfect amounts of each, you're probably going to have an excess of one, and the other one's going to be the limiting reactant. So I'm going to look at this, and I'm going to say, oh, liters times molarity, 0.6 is the liters, and I get 0.48 moles here. Liters in molarity, I get 0.24 moles here. Now, the next thing is, oh, 0.24 is bigger, so that's excess. Not necessarily. I didn't show this here, but if I took 0.48 divided by 3, I get 0.16, and that number is smaller than the aluminum chloride. 0.24 divided by 1 is 0.24. So I'm going to call this the limiting reactant. The silver nitrate is the limiting reactant, and the aluminum chloride is in excess. And what do we do with the limiting reactant? It all reacts. So 0.48 of this reacts, leaving me with nothing. And then I can look at my mole ratios. 0.48 of this reacts, so 1/3 of it reacts here, meaning 0.16 reacts here. Meaning 0.48 and 0.16 form, because 3:1 to 3:1 ratio is the same as 0.48 to 0.16 to 0.48 to 0.16. So essentially I'm taking 0.48 times 1/3 to get to this, 0.48 times 3/3 to get to this, which is the same number, and 0.48 times 1/3 to get to this. So at the end, I have 0.08 moles of excess aluminum chloride, I have 0.48 moles of silver chloride, and I have 0.16 moles of aluminum nitrate. Okay, it says identify the precipitate, which would be the AgCl. What mass of it's produced? Oh, I know the moles, I can find the molar mass, and then just multiply those together. So that step is pretty straightforward. And I just take the 0.48 times 143, which is the molar mass, and I get 0.69 grams. Okay, so here's how I showed how I got the limiting reactant, the excess. Thought I showed that someplace. Okay, what about the concentration of each ion left over? Well, just looking at this, all of the AgCl sunk to the bottom. Okay, so just looking at our picture, that is down here. So that's out of the picture. That's all at the bottom. That all sunk down. But we have our spectator ions, but we also have excess AlCl3. So I go back to my diagram, the precipitate's at the bottom, but I got my aluminum nitrate, my spectator ions, but then I also got that excess aluminum chloride, which is circled right here. So I have to keep track of all those pieces. And if the first one I start out with and find aluminum, I say, hey, I have aluminum here and aluminum here. I have to add those two sources. Notice I have 0.08 moles here. And what? It's in a 1-to-1 ratio. So it's 0.08 moles here and it's 0.16 moles here. So what do? I add 0.08 plus 0.16. I get 0.24. Now I have to divide this by the total number of liters in solution. And by coincidence, in this case, what did I have? 600 and 400, and that adds up to be 1,000 milliliters, which is 1 liter. So I take that, what, 0.08 plus 0.06, which equals 0.24, divided by the total liters of 1, and I get 0.24 M. Now, what do these brackets mean? The brackets mean concentration of. So that's a shorthand for saying concentration of aluminum plus 3 ion is 0.24 molarity. Okay, let's do it for Cl minus. Now the trick here is it's like the triple decker ice cream cone. If I have 0.08 moles of aluminum, I have 3 times 0.08 moles of chloride. Okay, however, I don't have any chloride over here, and we don't count this chloride because that was part of the precipitate. That's not floating around at the end. So what it ends up being is 3 times 0.08, 3 because of that 3-to-1 ratio, and then which is 0.24 divided by 1.0, and that ends up being 0.24 molarity as well, by coincidence. Okay, so the last thing is, okay, we've taken care of our aluminum, we've taken care of our chloride, we know there's none of this, this is all sunk to the bottom. We talked about the aluminum from here. What about the nitrate? Oh, the concentration is 0.16, but again, we have the triple decker ice cream cone effect, so we got to take 0.16 times 3, that balancer, and I say that is 0.48 divided by the total liters of 1, and I get 0.48 molarity. That would be the final concentrations of the ions left in solution, of all of them, including the excess limiting reactant, and I'd have 0.69 grams of AgCl at the bottom. So again, to review, I first balance my equation, figure out what's solid. Okay, next thing is I convert my liters of molarity to moles. I establish my limiting reactant as the AgNO3, figure out the moles of everything else. Okay, here I had to subtract to figure out the moles excess. Here I just went through my ratios. I knew this was my precipitate, so I just took this moles times the molar mass to get to grams right here. And then I had to add up the concentration of all ions. Notice this I ignore because there's nothing left. When I'm doing ions, this I ignore because it was all part of the precipitate. But I had 2 sources of aluminum, so I added up the 0.08 and the 0.16, divided that by the total liters of 1 to get 0.24 molar. There was only 1 source of chloride that was in solution. This was all part of the precipitate. but this was a triple decker cone. So it was 0.03 times or 0.08 times 3 is 0.24. And I divided that by total liters to get 0.24. And then there was one source of nitrate, and I took what? It was 0.16, but I times that by 3 because it was like a triple decker cone. And I got 0.48 over 1, which gave me 0.48 molarity. All right, hope that helps. A lot to keep track of. Thanks for watching.